Okay, so yeah, I think in the last lecture we talk about another phenomena that we typically see in the later stage of the precipitate growth processes, which is the outward ripening. So if you still remember what this is, if you start with smaller particles in the system, or you start a distribution particles, as the precipitates in the system. But as the system evolve, what you will see is that the large particles will eat up the smaller particles, and this will lead to, number one, a decrease of the total number of particles or precipitates in the system, and number two, the average size of the particles measured as the, for example, average radius will grow. Okay, so we call this the outward ripening processes, and we, I think the last lecture showed that this is again due to the Gibbs-Thomson effect, because you have particles of different sizes or different curvature, so their effective Gibbs free energy are different, and this will lead to different equilibrium composition of the solutes, right, in the region, in the alpha phase region, right near the particle surface. So basically, if you have large particles versus smaller particles, the solute concentration in the region, in the alpha phase region, immediately near the smaller particles is much higher than that in the larger particles. And this will lead to overall flux of solutes from the smaller particle to the large particle. Okay, so, and once the alpha phase region with, near the smaller particles, in short of the solutes, they're going to take extra solutes from these precipitates, right? Because basically why these beta particle form is because when you decrease temperature, the alpha phase, basically the solubility of the B atom in alpha phase decreases. But because now, if the local alpha phase are not oversaturated, so these beta particles can melt back again, right? So if like that, you have a sugared water, and if you take a lot of sugar away from the water, suppose that there are mechanisms you can do that, and the precipitated sugar can melt back. So that's the same thing. And the large particles keep on grabbing the solutes from the smaller particles through the alpha phase, through diffusion, and basically the smaller particles going to shrink and shrink, the larger one's going to grow and grow. But as the smaller particles keep on shrinking, the Gibbs energy going to be higher. And then this is kind of a positive feedback, right? The smaller, as you become smaller, you're gonna lose more solutes, and so this process continues until the smaller particles are completely gone. That's the outward ripening. Again, this is due to the Gibbs-Thomson effect. So I think we derived this equation, which is the overall kinetic equation for the outward ripening. Basically, the I think we don't have to go through the detail again, but the consequence is that if you keep track of the average particle radius in the system, this average particle radius, the cubic of the particle of the average particle radius is going to scale linearly with time. Okay, this is a very typically seen diffusion controlled coarsening processes. Okay, so that's basically the Gibbs-Thomson effect, and we show some experimental evidence for, the outward ripening. We show some experimental evidence for this. And that basically completes our discussion for the different stages and different processes during the precipitation, right? So we start with nucleation and focus on both heterogeneous nucleation and homogeneous nucleation. And then we focus on the precipitate growth, especially the one that nucleated on the green boundary, and we show that basically we can decompose the growth into two almost independent modes. The thickening and the lengthening, they're governing by different diffusion controlled mechanisms, and they have a completely different rate of growth. And also, during the later stage of the growth processes, we need to worry about the outward ripening, and you can typically see these type of effects for the particles nucleate or precipitates nucleate, in a homogeneous fashion within the bulk, or for some other systems, you see a lot of these particles nucleate simultaneously, and we have this very strong effect of the ripening that governs the overall evolution of the microstructure. So that's basically the typical processes we need to deal with for the precipitates, and for the precipitates nucleation growth. Now, So after this, one thing we're very interested in, which is relevant for, microstructure engineering, is that, we know all these different mechanisms that can control the microstructure, right? And you probably, if you impose proper condition, temperature, and you wait sufficient time and you see the transformation going to complete. But for example, if we don't want all of the large amount of beta phase, right? We want to stop the transformation by freezing the system in some intermediate microstructure, and so that we can have a better mechanical properties. In order to do that, we need to have a better picture of how the transformation, or how the overall amount of beta phase, right, change as a function of both time, and also we want to know if we change temperature, how this is going to change the overall transformation processes. So this motivates us to consider or construct the so-called TTT diagram, which means temperature transformation and time diagram, or temperature time transformation diagram. But basically, it collects all the information and all the parameters, effect of different parameters that we just mentioned and of interest to us, right? So in this case, like in all of the transformations, we know that temperature definitely going to play a role, right? But for a given temperature, okay, as the time proceeds, we also see the transformation proceeds. So basically, the TTT diagram allow us to collect all this information in a very schematic way, onto a kind of universal diagram, so that we can easily analyze and use that information to design microstructure. Okay, so for example, what I'm showing here is a one way of presenting the TTT diagram. So the horizontal axis basically is your time axis, but because the transformation usually do not work on a linear scale, so we use log scale, but it doesn't really matter. Okay, it's basically the horizontal axis is the time, and vertical axis is a fraction of the phase that has transformed. Okay, I think we talk about in detail, and from the phase diagram for given temperature, okay, like T1, and if you go to the phase diagram, you can compute what will be the equilibrium amount of this beta phase, right? So now this F is the fraction of the phase that has already transformed over the predicted equilibrium amount. So if the transformation is complete, right? If you wait sufficiently long time and the transformation complete, what you will see is that this fraction approach 1. This means the system is in equilibrium. All of the phase that can be transformed has been transformed. Okay, but this takes time, right? So now, if I do not wait for that long time, I just stop the processes in a short period of time after the transformation starts, I will get just a fraction of all possible beta phase, right? So this is basically give you the fraction f. So it goes from 0 to 1. So that basically tells you for a given temperature T1, right, for a given time, how much of the beta phase that can be transformed has been transformed. Okay, so that's just basically the information that you can get. And if you go to a different temperature, for example, T2, which is lower than T1, right, you presumably going to see a different curve, because number one, it takes a longer time for the precipitate to nucleate, right, because you have a higher temperature, higher temperature, I think this is T2, is higher than T1. So the supercooling is lower, right? Smaller. It takes longer time for the beta phase to nucleate. And also because the driving force is smaller, the transformation process itself is very slow, or slower than this one, than the lower temperature. So you see that this curve starts later and is more kind of stretched along the time direction, meaning that it takes more time, right? This amount of time for the transformation to complete. So that's just a kind of a initial impression of the TTT diagrams. Okay, so I think I showed you this animation, which is hard to make it work, so I won't show this again. But this is another ideal example that I have. In this case, all my alpha phase, for example, going to eventually transform to the beta phase. I have a solid phase which is completely taken over by a different solid phase. And in this process, we see that, we can have particles of different sizes pop up in the system and they start to grow. But in the early stage, every particle just to grow like a circle perfectly. But eventually the particles near to each other, they're going to have this impingement, and then they're not going to grow, freely as a circle, right? They're going to have constraints, and then you have some, these polyhedral type of geometry formed in the system. Okay, so the reason why I'm showing this is that we want to use this very simple ideal model to try to understand what is the generic mathematical form of this function that is crucial to the TTT diagram. Okay, so that's what we're gonna do, and I think we already started a little bit, but I just want to give you a quick recap. Okay, so basically this is where we left, right? So we introduced the idea of the TTT diagram, and we want to find in general what is the mathematical form for this f function. Okay, so now to do that, of course, you can always do experiments and measure the fraction, but this will be a little bit time consuming, and sometimes you can get large fluctuations or not consistent results. So to do that, I think the first thing we can try is to start with a very simple model, right? And try to get some insights from the simple model, and then we connect this to the experiments, and then we can get much better picture of what's going on. So we start with the simple model. Okay, again, the idea is that, okay, so initially I have this alpha phase, which is this box, and then I start to nucleate some beta particles, and in this case we are assuming a scenario which we call the site saturation scenario, meaning that all of the beta nucleus can occur in the very beginning of the processes, and it occurs simultaneously, which means that all of the beta nucleus can emerge in the beginning and then just keep on growing. There will be no nucleus formed during the growth processes. We call this the site saturation scenario. Okay, so now this picture will be very straightforward. They have some nucleus formed in the beginning of the processes, and they all keep on growing. And we want to work out, at least in the beginning of this process, right? When the particles are far away from one another, there's no impingement. What is the fraction f gonna scale as a function of time? Okay, so to do that, we first work out. In this case, we just simply assume we have circles in 2 dimensions or spheres in 3 dimensions. So and the fraction is simply the volume fraction of these beta phase, okay, within the original volume, right? So that's very easy to compute. So in order to compute the volume fraction, we first need to compute the volume of each particle as a function of time. And this is very straightforward because they're circles. So we have this 4/3 times pi r to the cube, right? But because r, which is the radius of this particle, is a function of time, and we impose a constant growth velocity for the radius, right? And v times t simply gives the radius of the particle at a particular time t, right? So all this together gonna gives you the volume of the particle. And in order to compute the the volume fraction, what we need to do is to simply divide this volume by the total time. This is the volume of a single particle, right? So we need to times the total number of particles in the system, which is n, okay? And basically we use this and divide it by the volume, the total volume of the system. This is what we need to do. But in most literature, okay, this is exactly what we are looking for. But people actually introduce a little bit fancier way of doing this. For example, they combine this n and vt term. So instead of having n times v first, we first define a quantity, what we call rho, okay, which is the number density of the particles. Okay, and this quantity is defined as the number of particles, okay, per unit volume. So you just compute it as you take the total number of particles and divide the total volume of your system. This is called number density. Okay, the number of particles per unit volume. Why people use this is because this is consistent with the nucleation analysis. Because for nucleation, we always talk about number of nucleus per unit volume. So this is basically inherent from that analysis. But anyway, once we realize this or introduce this number density, it's very easy for us to see, right, that the f, which is the fraction of transformed beta phase, can be easily expressed as rho number density times the volume of each particle, right? This is very clear. So if you plug everything, we see that, this f as a function of time is given by this expression. And so all this part is a constant, right? So this v is a constant growth velocity, maybe depending on time, and depending on temperature. Rho, again, is a constant for a given temperature, and time is basically the only important parameter that governs f. Okay, so we see at least for this site saturation model, okay, for T is small. In the initial stage of the growth processes, we see that the fraction of the transformed phase scale with the cubic of time. So this means that initially the fraction going to increase very quickly. Okay, so this is basically what we see. And if you keep in mind of the scaling relation and go back to the plot that we have, you see that during the initial stage, the fraction indeed grows very quickly. And this growth is very much like a power law growth, right? So this is basically initially, this is f is scaling with t to the third power, okay? But it's log t, so probably we're just looking at the initial stage here. But anyway, that's from this very simple saturation analysis. So now this is not the only scenario that you have a growth processes, right? We say in this case we assume all the nucleus, they all form in the very beginning of the processes. They just suddenly emerge and no more nucleus is going to form. And this particular scenario gives us this cubic scaling of f with respect to time. So now let's look at another scenario, which I think is more realistic. Okay, this scenario is called cellular transformation. Okay, so again, this name is not quite important, but the important thing is the physics or the scenario, how the nucleus emerge. Now, in this case, instead of assuming that all the nucleus is going to form simultaneously in the beginning of this processes, we assume that the nucleation can occur, okay, throughout the entire growth processes. This means that if you were able to, okay, divide this whole processes into very small time interval, and you will see that in the first, in the beginning of the first interval, you have some small nucleus form, small number of nucleus form, and this nucleus is going to keep on growing. And then later, you're going to have, at the next time frame, you're going to have new nucleus, small nucleus form, okay, and the already formed nucleus is going to keep on growing, but you keep on producing new nucleus as this process proceeds. Okay, so basically in a more rigorous mathematical statement, this means that we have a constant nucleation rate throughout the entire transformation. This means that we have a constant number of nucleus emerge per unit volume, per unit time during the entire processes. Okay, so that is what we call the cellular transformation. And you can see probably this is a little bit more realistic than the saturation scenario we described, right? Because there's no reason to believe that all the nucleus has to form in the very beginning and new more nucleus form. In general, you're still going to see small nucleus form, throughout the entire transformation processes. Okay, so now how we should deal with this scenario. So again, the basic idea is that you want to find out, what is the volume fraction of the transformed beta particle, right? And this is, you take the total volume of the beta particle, but divide the volume of the entire system. But in this case, how can you compute the total volume of the beta particle? Each beta particle have different size in principle, right? How would you compute that? Okay, so just take that. So, and because we know that the reason why that these beta particles have different sizes is because they form at different time point, right? So assuming that, okay, let me show this, which I hope I can. So basically we have a time axis, right, that we go here. And then what you have on this axis is that, let me use this. You have, so now I'm actually, I'm observing at this time t, right? And basically this is my starting point, which is 0, right? And within this particular, interval, at any time tau, okay, I'm going to have some nucleus form. Okay, I'm writing this. Okay, so now if this nucleus form at 0 in the beginning of the processes, now if I make an observation of this nucleus, what is the radius that I'm going to see for this guy? The radius is going to be v times t, right? Because this nucleus formed in the very beginning at t equals 0, and now it grows for all this time. So the size of that nucleus is going to be v times t. This is clear to everyone? right? I hope it's very clear, right? But now if we look at the nucleus, which only form at a later time, which we call tau, right? Which is this point. If I have a nucleus which formed at this point, tau, okay, so at the time of my observation, this nucleus only grow for a smaller period of time, which is given by this one. So what's going to be the size of that nucleus formed at tau? Again, we take the constant growth velocity, but what is the time it used to grow? It's t minus tau. Does this make sense, everyone? Right? Because if I have a nucleus form at this particular time, it only takes this time to grow. So the radius is going to be smaller, okay, than the nucleus form earlier than the sky. Okay, does that make sense to everyone? Okay, but nonetheless, if we realize that, okay, we can always write down the expression for the volume for all the particles that, for all the nucleus or all the particles that nucleated at this time tau, right? For those set of particles, okay, the radius are simply given all by this v times t minus tau. So I just plug in the volume, I get this. This is the volume for all the particles that form at tau, if you look at them at time t. Is this clear to everyone? Okay, so now if this is clear, this is only for the particles that form at tau, right? But now what we need to do is that we have to consider all the particles form at different tau, right? My tau can equals to 0 and all the way to t. So I need to sum over, the volume of all these particles, and that's gonna give me the total volume of the system. Now, how could we do that? Okay, because we know the nucleation rate, right? We know that for during time dt, okay, this number of particle gonna form. So we have this information, okay? So this means that during each time interval, I'm going to have a constant number of nucleate form at a given time, tau. Okay, so combining these two information, okay, what we can do is that we sum over all of the particle together, right? So the volume of all the particles together nucleate at a different time, right? So in order to do that, we have to sum over all these time together because, this means the particles nucleate at this particular time. And if you look at that, this is the number of that particles nucleated at the time. Okay, let me write one more equation for you. Okay, so this is, for example, if we're looking at tau, right? So this is the volume of that particle nucleated at tau if we make an observation at time t, right? But what is the total number of such particles of this volume? And if we're assuming that we have a constant nucleation rate, which means the number of particles per unit volume, per unit time, and this is going to be, okay, the, roughly speaking, the number of particles that nucleated at time tau, okay? So basically now what we need to do is that, okay, for time tau, how many particles I have? I have this number of particles, right? But each particle going to have this volume, which is v prime t, right? This is only for a very small interval near tau, right, dt. So what we have to do is if we want to find all of the particle volume, we need to sum over all of these smaller intervals, right? Sum all of these smaller intervals. But if we assume that dt is very small, the summation is going to become integration. Okay, so basically what you need to do is that you're going to integrate all of this up to t, right? So sum over all these small intervals up to t. So this is what you do, okay? So, but if you plug in the expression that we already derived, and you'll see that only t-dependent quantity going to be this one. Okay, this is going to be tau because this is going to be a function of tau. So we're doing this. Okay, so basically this is where it comes from. Okay, again, very straightforward. We're trying to find out the total volume of the particles in the system, but the particles nucleated at different time can have different size. We take into account that, and then we sum over all the particles through time. Okay, so that's basically what we have here. And once we reach this expression, the next steps will be very straightforward. We just, do the integration. It's very straightforward. It's power law, and we get that out. And I won't go through the details. Very straightforward. And after some simplification and plug in 0 and t as two extreme values, you're gonna get this expression. Okay, so now if you compare this expression, if you remember, okay, compare this expression to the previous expression that we derived for the set saturation processes. Okay, you see that the constant, of course, are different. Okay, but the key difference is that if we have a different mechanism for the nucleation, okay, because in here, if you look at the major changes will be, I change how the nucleus form, right? In the previous case, I assume that all the nucleus is going to form in the very beginning of the processes, but in here we show the nucleus is going to form throughout the entire processes. Okay, these are two different kinetics for forming nucleus. We see that this is going to change the scaling of the fraction, of the transformed fraction as a function of time. Okay, the constant, of course, is different, but we're more interested in the scaling. Okay, so now if you compare this scaling for the site saturation case, for these two, okay, so now my question for you, at least to think about, is that if T is small, okay, so if we look at it in a very early stage of the nucleation process, when T is small, now which scenario going to give you a larger or faster transformation? Is the site saturation going to give you a faster transformation when T is small, or the cellular transformation?
Wouldn't this case give you faster transformation because t to
You
the
mean
fourth?
when T is small? The key is when T is small. So this means that T is smaller than 1,
Oh, then it would be t to the third.
right? So initially, so basically when T is small, you see that this saturation will give you a faster transform. Why is that physically? Well, because you produce basically all the nucleus in the very beginning of the processes, right? So because you start with much more particles to grow with. So initially, you're definitely going to have a much faster growth compared to this. But when T is greater than 1, so when T is large, you see eventually this mechanism going to win. The reason is that because if you all start with the particles that in the system, as T goes further and further, they're going to have impingement. Okay, and it, from the packing, right, when you have particles of different sizes, because the smaller particles can always fill the hole. Okay, now this is not a rigorous argument, but this is one interesting way imposed by the different transformation or nucleation dynamics. Okay, but anyway, so this is what we learned from this very simple analysis. One key thing I want to point out is that all of this analysis is only applied to the very beginning of the transformation processes, where we assume that either the particle have no impingement or the impingement is very small. But eventually, when the particles grow larger and larger, it's going to affect each other, going to stop the growth of the other particles right in its way. So this is going to cause complication of the F. You're going to change the scaling behavior. Now, without going through the detailed derivation, which I reserve, I think, as a homework problem. But anyway, for now, I would just directly provide the results. Okay, it's very easy to do that. We just need to construct a differential equation for F. Consider what we had discussed, but in a differential fashion. You can easily construct a very simple differential equation. But anyway, so I reserved this in the homework, which I give you sufficient hint to do this. So for now, I'll just give you the results. So if we have the impingement, right? So our initial analysis of this free growth of the particle not going to be true, right? We have to consider their interactions, all the other stuff. But eventually, you can still solve this problem, which is not very difficult. And the final solution, okay, for this the cellular transformation scenario is that, okay, now if you want a overall picture for how this fraction of transformed fraction change as time, you get this guy. Okay, so it's not a simple power law, it's a exponential function, and within this exponential, you have a power scaling. Okay, so again, whenever we have a result like that, we always want to check, okay, so is this mathematical results consistent with our previous simple analysis? Okay, this results agree with what we already derived in the limit when t is small or in the early stage of the growth. So what we can do is, number one, we can check what happens to this equation when t is very small. Okay, so this will correspond to the early stage of the system, right? So now if we t is small, okay, all of these part is a constant, right? When t is small, this means that t raised to the fourth power is going to be even smaller. So the whole thing in this one going to be very small. Now I call this x. I group all of these stuff, okay? I call this x. So basically what we have for now is simply e minus exponential, okay, and minus x. When x is very small, or when x is very close to 0, okay, you can do a Taylor expansion of this exponential function. Do we know what is the Taylor expansion of this exponential function when x is small? It's simply 1, right, minus x. Okay, and plus higher order terms, but we just keep the first term. This is the Taylor expansion of this exponential minus x when x is very close to 0. Okay, and then you plug this back in here, you have 1, right, minus 1 cancels one another, and plus x. Okay, so this means that when x is very small, which means t is small, okay, the whole term within this exponential is small, okay, and we're plugging this in the expression, okay, you can get a simplification of this f of t as a function of t when t is small. Okay, so this is very straightforward. Let me erase this and shows the clean result. Okay, so that's basically what we do. And if you use that Taylor expansion, okay, it's very straightforward that you recover, okay, the simple expression that we derive altogether from this very simple geometrical analysis. Okay, so this is consistent. And on the other hand, if t is very large, okay, when t goes to infinity, so this means that, okay, the system has to achieve equilibrium. Okay, and in this case, we consider the whole system has already completed its transformation. So f has to equals to 1. And again, this is consistent, right? Because you have a minus positive large number, and this second term as t goes to infinity goes to 0. So you're going to recover 1. Okay, so this is very consistent. So if you look at what this function looks like, if you plot this as function of time, okay, this is ft as a function of time. Okay, this thing going to look something like what we exactly see. You see star grows and then asymptotically approach 1. Okay, so this is that. Okay, so you see that we, through this very simple scenario, and we, kind of get some information about the mathematical form for this function. Okay, but there are another, two important considerations that we haven't touched upon. Number one is that how we can introduce the factor of temperature in this analysis. We always say that in our analysis, we keep the temperature as a constant. But but if we look at the physics, where do you think that the temperature is going to get into, the parameter in this equation? What temperature? If we change temperature, what do you think the parameter is going to change? Okay, there are only two physical parameters besides time. The first one is n, which is related to the nucleation rate. The other one is v, which is the growth velocity. From our previous analysis, from all of the lectures where we already studied, do you think that these two parameters are going to depend on time? I'm sorry, on temperature? The answer is yes, right? So we have been gone through the analysis all the way up to here to appreciate that these two kinetic parameters is and it's very sensitively depend on temperature. Okay, so this is for basically this means that we fix temperature T, and then this is how the fraction of transformed phase gonna looks like as function of time, right? But don't forget these key kinetic parameters that in this exponential form depend very sensitively on the temperature. So this is where the temperature comes from. So you have velocity depend on the temperature, and also nucleation rate depend on temperature as well. Okay, so that's that. And another thing is that, okay, how generic this mathematical equation is, right? Because in deriving this equation, we have assumed a very particular nucleation scenario. We assume that the nucleation can occur at a constant rate throughout the entire processes. Now, in general, this may not be true, right? The nucleation may actually occur faster in the beginning and slower at the end, etc. So, this will, in practice, there's no, guarantee that you're going to have exactly this scenario. Now, if we have a different nucleation kinetics, where do you think we're going to modify or change the equation? Okay, so without spending too much time on this, we see that when we change the kinetics of the nucleation, this scaling change, right? So for the saturation case, we have t raised to the third power, but for this cellular transformation, we have t raised to the fourth power. So this implies that if I change, in general, the nucleation dynamics, and then I can change this power in time. Okay. So now with this understanding and analysis, we can actually take our results and generalize our results to a generic form for these transformation. Okay. So we may have different, kinetics and different nucleation scenario, but in general, it's based on our previous analysis, I think it's quite safe to say that the overall transformation fraction f has this generic functional form as a function of time, but also depend on temperature through this kinetic parameter k, right? We don't know what the k looks like in general, okay, but we know that all of the experimental data should actually follow this generic mathematical form. So we can actually then take a logarithm of the data, do the scaling analysis, and compute what is k and what is n. Okay, so this empirical relation, which again has a very deep physics justification, as we just show from some model scenario, right? Is called the JMAK equation. Okay, the name is there. I wouldn't read out for you, but it's JMAK equation. It's very well known in metallurgy and this alloy solidification community. Okay, so basically this equation is powerful enough to almost describe all of the different types of transformation kinetics by choosing correct temperature dependent kinetic parameter K and this nucleation kinetic dependent power N for the T. Okay, so that is basically what we're looking for. Okay, so if you still remember when we introduced the TTT diagram, okay, we say that we have this generic, we have the this information of the transform the fraction of the phase of interest, and have this generally this typical form of the f as a function of time, but we want to work out what is the more detailed mathematical form for this. Okay, and we go through two simple nucleation scenarios, and then we get a general expression, and we further generalize this, and we reach the JMAK equation. So this is what we're looking for. Okay, so in general, it doesn't really matter what material you have, doesn't really matter what is the nucleation kinetics, doesn't really matter what is the growth kinetics. You're always going to have this JMAK equation that be able to describing the fraction of phase that has been transformed as both a function of time and temperature. Okay, so that's just basically very crucial part for the TTT diagram construction. Okay, so I think this is clear. Okay, now once this is clear, I think we basically have all the mathematical ingredients we need to construct this, right? So we can just use this equation, and given experimental data, we can do fitting, we can do a lot of calibrations for the parameters. Once we have all of those information, we can collect them together, okay, into even a different form. Okay, so this is another form of the TTT diagram. The basic idea is that we have to connect fraction of transformed phase to temperature and to time, right? So we have been working on this scenario on the bottom, which shows the curves like that. So in this case, we fix temperature and we see how the phase transform as a function of time. But there are different ways that you can look at this, right? We can actually look from the top, okay? So if you think about this, these are functions, right? So if you look at this as a plane, these functions kind of stand out. with different heights, like mountains or valleys, things like that. Now, what we can do is that we can look at a different way. Okay, we instead of plotting f as function of time, what we do here is that we plot we keep the horizontal axis to be time, but my vertical axis to be temperature. Now, in this case, basically what you do is that if you fix temperature, right? Okay, this is going to be like this. If you fix temperature as time proceed, you're going to have different fraction, different amounts of the phase transform, right? So basically what you do is that then you do the mapping here. So say this is like 1% transform and you label it right here. And this is 99% transform, you label it here. Okay. And then you can choose a different temperature, for example, and do the same thing. So, and if you connect all these lines together, okay, so these lines in this T temperature and time diagram basically tells you these lines along each of the line. Basically, this tells you this is the equal fraction line. Okay, this is not equal temperature line, but equal fraction line. This means that, okay, at this temperature T2, okay, for this time, this is a particular time. Let me just do that for you. So I can choose a number of different times like these two, right? So for this temperature T2, right? If I compare T2 versus T1, okay, at T2, okay, at this temperature, I have 1%, of the solid phase transform, but I have nothing transformed at T1, okay? So now if I look at a later time, okay, so in this case, for T2, which I didn't have a curve shown here, but I think I can do that quickly. Okay, for T2, suppose this is a 50% equal fraction line, okay? So for T2, for this temperature at this time, I have 50% of the transformation that has complete. Well, for the lower temperature, you only have 1% because this is the intersection with the 1% line, okay? So that's basically what's going on in the system. So again, you have a different way of looking at this information. You can either look in this way where it shows you at different temperature how the fraction of transform change as a function of time, or you can look at it in this way. Okay, so I think this is a more commonly used way to represent the TTT diagram, and here is just a example of more beautiful illustration of the same concept that we described. Okay, so yeah, again, I won't tell more detail about the TTT diagram, which I think is more appropriate for the subject of a physical methodology class. But for now, I just want to introduce the concept. We know that there's a diagram tell us the information of the transformation, including kinetics information and what is the underlying equation that consider both the transformation kinetics as well nucleation kinetics together. Okay, so I think that's pretty much all I want to say about this TTT diagram. Again, this is what we described in this lecture. In the last lecture, we talk about all-square ripening, which is kind of a final stage processes in the solid-solid phase transformation. We understand the driving force and the kinetics, and then we talk about the overall transformation dynamics and introduce the TTT diagram to very conveniently quantify that. And we introduce the JMAK equation, which is kind of the mathematical core underlying the TTT diagram. Okay, so I think that's pretty much all I want to say for these topics. Do we have any questions? If not, let me switch gear. Okay. Well, by the way, I checked the schedule. I think I posted the final exam schedule. I hope that up in the updated syllabus on Canvas. I think we are doing the final exam on the Tuesday of the final exam week in the morning. I need to double check the time, but I think it's probably earlier than the lecture time. We have 2-hour time frame for this. So for the in-person, students, suppose in quotation mark, we're gonna simply use this time. Okay, so I will do probably something similar to what we did in the midterm exam. I'll just send you individual emails for a copy of the exam, and I'm going to shuffle the questions. So Each one may have a different question, but with roughly the same level of difficulty, may change of numbers and things like that. And I give you, so I think the official window is roughly 2 hours. I'll give you a little more than that, so you can have time to, if you want, download the exam, print it out, and also I give some time to scan the solution and send back to me. So that's my initial idea of doing this. But certainly we can discuss this, and I can make accommodation if you need to. Uh, and for the online students, I will have to make separate arrangement, because for the midterm, I think most of the students cannot actually work on the exam during this working day time. So I'll make separate arrangement. But anyway, so that's the plan for the final exam, and we still have quite a few lecture ahead, and I think we're okay. So I will again devoted at least one lecture as a review lecture, as we did in the midterm, to go through the key concept and the examples that you may have actually seen in the final. Okay, anyway, I'll make an announcement and about this probably later this week. Okay, anyway, so now let's switch gear. Okay, so and talk about another solid transformation, but it's quite different in terms of.
Can I ask one question related to exam?
Yeah, sure.
Yeah, is it on 27th or is it on 29th?
I think it's on Tuesday. On
Oh,
the
okay, so
Tuesday, so it will be
27th.
27. Yeah, so it will be 27th. Yes,
Okay, thank you.
no problem. Thank you. And it will be in the morning. I think it starts from 9 something, but I need to double check. I updated the syllabus, so the information is there, but I will highlight those information for you in the announcement. Anyway, so yes, so yeah, so we talk about the precipitation growth, which is a very classical example for solid transformation. And in that, I think we kind of see the normal way how the energy barrier and driving force and the kinetics that play a role altogether in determining the growth kinetics. Okay, so now we're going to talk about another example of solid phase transformation, namely spinodal decomposition. Okay, so now we're going to see that in this one, we see a lot of not so intuitive effects going on here. Okay, so this transformation is very much like spinodal in certain, I mean the eutectic in certain sense, but not quite. Okay, and it has very interesting kinetics, which means that the motion of the particles, the flux of particles, are not driven by diffusion or random motion. Again, not driven by I would say gradient-based diffusion. Is actually driven by the chemical potential. Okay, so you see some very interesting consequence of this. And again, yeah, we just describe the kinetics, driving force, and barrier. Okay, so and this is another very commonly seen type of transformation in solid systems, and have a lot of realizations, especially in copolymer systems and those type of things. So it's quite useful and interesting to look at. Okay, but anyway, so this is the spinodal decomposition. Okay, so now what is spinodal decomposition? Okay, so to just give you a rough idea, I think the image on the left shows very quickly, but I think in a replay, if not, I'm going to do that. Okay, so basically you start with, this is basically spinodal decomposition. Okay, it's so quickly, so I probably won't see the initial. In the initial, you have kind of purplish, homogeneous mixing of red and blue. Okay, and each color gonna denote a different composition of your solutes. Okay, so now if you look at the thermodynamics of these processes, which is quite straightforward, and we have seen this many times, we have a phase, not a phase diagram, but a free energy curve. Okay, so this is a free energy of mixing. Again, this all of this you can basically consider were based on the regular solution model. Okay, you have a free energy of mixing. Okay, when temperature is very high, right, we have this single local minimum. But as you lower the temperature, we know that we're going to have a double local minimum free energy curve. The reason is that you have competition between entropy and enthalpy considerations, right? But whenever you have this double local minimum, we know that thermodynamically the system wants to separate in two different phases, favoring different distinct composition, A1, A2. Well, but overall, there's still one microstructure, but two distinct composition. Okay, So that's basically the free energy and phenomenologically what happens for the spinel decomposition. Okay. Now kinetics, what you see is that you start from kind of homogeneous mixture, and then the phase start to separate, and they keep on growing, and one of the phase become coarser and coarser, and the other one also become coarser. So that's basically the overall kinetics. Okay, so that's spinel decomposition in a nutshell. Now we're trying to understand what's going on here. Okay, so this is like a kind of a snapshot. Okay, not taken from the previous image I showed, but it's from a similar simulation. Okay, you start with a very fine-grained mixture, and then each phase gonna keep on developing, and they're getting coarsened, means that the average linear size of the ligaments is increasing, um, etc. So this is the spinal decomposition processes. So basically, this means that you have a system for which the free energy has two double or local minimum. And if you prepare the system in a composition which is thermally unfavored, it's going to undergo a simultaneous phase transformation, in the sense that the solute is going to redistribute to favor two distinct composition. Okay, so that's spinal decomposition. Okay, now clearly the mathematical, the thermodynamics model for this is the regular solution that we have spent a lot of time on. But since it's already been quite a few months, I guess, at least a couple of months, so I guess it's useful for me to give you a very quick recap of the thermodynamic consideration for this. Okay, so again, this is the regular solution model. Okay, and here I show gas, but I know that we initially we used the solid solution, but is idea is straightforward. We have A and B as pure system, but if you mix them together, you get a mixture, right? And we want to compare, which one is more stable thermally, right? So this corresponds to the phase separate state, and this one corresponds to the mixing state. And the way we do that is that we get we get the free energy of mixing, okay? And this composed two terms, the enthalpy of mixing and the entropy of mixing. And for the case of solid solution, we were able to write out the for the ideal solution, and we and also for the regular solution, we're also assuming this works, is that we can have the expression for the entropy of mixing. Okay, so for ideal solution, if the only contribution is going to be the entropy of mixing, we know that it always favors mixing, right? Because this entropy of mixing always going to be positive, but you have a negative sign in front of this T times delta mix S. So this is always going to give you a lower free energy. So if the system is completely governed by entropy, it always favors mixing. That's the ideal solution. And for the regular solution, you have to, and we work out the enthalpy of mixing, but also using kind of simple example. And in this case, we're assuming that all the atoms have a random type of mixing configuration, so we get some average consideration. Okay, if you have a superalloy which gives you ordered configuration, we know that this will be a different picture. Okay, but so this expression for the enthalpy of mixing only work for the case that you have random mixing of atoms. Okay, so basically you break some A-B bound, you form some A-B bound, and basically what you get, the enthalpy of mixing depend on the molar fraction of both A and B atoms through this equation, and this capital lambda, or we have used omega, but that's the same thing, depend on the bonding energy between AA, BB, and AB. Okay, that's the same thing. But the interesting thing is that now, because you have this interaction parameter lambda, and this guy can be either positive or negative, right? It can also be zero, but when this guy goes to zero, we're going back to the more trivial ideal solution case. So typically, when we talk about regular solution, we will set this lambda equal either greater than zero or smaller than zero. Okay. And then you have basically two scenarios. When this delta H mix or delta mix H is smaller than zero, physically, what this means is that energetically, the particles also favors mixing, right? Which means that if you replace AABB bound with AB bound, the AB bound even have a lower energy. So the system is very happy to be in this mixing state. Okay, and on another hand, if delta mix H is greater than zero, this means that from the energy point of view, the system does not favor mixing, because you increase the interaction energy by replacing AABB bound with AB bound. Okay, so these are the consideration from the entropy, right? enthalpy. Now for the free energy, we have to combine these together, right? So and so the delta, the free energy of mixing gonna be a combination or sum of the enthalpy of mixing and the entropy of mixing. So we add up these two together, okay? And if we have the interesting case, which the enthalpy does not favor mixing, but entropy does favor mixing. And this is the case that we're going to have a lot of interesting phase behavior, right? Because if you have this delta mix H smaller than 0, okay, both entropy and enthalpy favors mixing, so you're never going to see a phase transformation. You can always get stuck in this mixing state, which is a very low energy state. But if your enthalpy does not want to be mixed, the entropy wants to be mixed, you set up a competition, right? Which one gonna win? Which effect gonna dominate depend on the temperature. So basically, in this case, by changing the temperature as a knob, you actually induce a mechanism for phase transformation. Okay, so that's basically the thermodynamic consideration for the Spinolo decomposition. Again, we see that this is a scenario when temperature is very high, so the entropy actually dominates the system. So when you add up this enthalpy term together with the entropy term, which is very negative, all of the free energy are negative, right? So basically, this means at very high temperature, the entropy going to dominate, and you still favor mixing for the system. Although energetically, you do not want to do that, but because the entropy dominant, so you're still going to mix. Um, but the interesting thing is that in this particular case, as the temperature start to decrease, okay, we'll see that eventually the contribution of entropy are not, let me do the notation. Eventually the entropy will not dominate the system. So what you're gonna see, if I remember correctly, you're gonna see something like that. Okay. So there will be a range of composition, okay, within which if you force the system to mix together, you're going to increase the overall free energy. And we know that thermally, if your composition is within this range, the system will not be thermally stable as a mixture. So they want to separate, right? Separate into two different, composition, okay, which going to give them a lower free energy. Okay, so that's basically uh, uh, what we're actually working now. Okay, so this is the thermodynamics. Let's move on. Yes, so that's the entropy of mixing, right? A free energy of mixing. So now if we want to get the phase diagram, we have to go back to the overall free energy of the system. So this is very straightforward. We just add the free energy of the mixing case as a reference, and then we have the total free energy again. Okay, and we did a lot of analysis for this, and we get the chemical potential, activity, etc. But I wouldn't go into that right now. Sorry that I think I lost connection for I don't know how long, but I forgot to unmute myself. But anyway, so let me see. No, I think we're on here. Yes. So yes, but if we're given the free energy curves, right, and we can do the double tangent construction or Maxwell construction to find out the equilibrium composition for any temperature right? And then we can map that information to the phase diagram, and basically we get this. Okay. Now, if you look at this process, this is very familiar to the one of the homework problem you have actually worked out. So that's exactly the same thing. Okay. So again, this is a thermodynamics about spinel decomposition, right? You start with regular solution, and you have a competition between entropy and enthalpy. When temperature decreases, the enthalpy gonna dominant, and you begin to develop two local minimum on the free energy curve. And then this indicates the system wants to be separated into two different phases. Based on that information and the Maxwell construction, you can have the equilibrium composition for the two phases, and you have the free energy. And based on the free energy, you have the phase diagram. Okay, that is what we know about the system. Okay, so now we're gonna look at this free energy curve and the phase diagram in a little bit more detail, because when we first do this, the only thing we take into account is thermodynamic considerations. We say that this is a phase diagram purely based on the local minimum and Maxwell construction of the phase diagram. But now we're going to looking at some more detailed information, especially in connection to the kinetics. Even we know the system wants to separate into that particular, x1, x2. Is there any barrier that stop the system doing this, or in terms of kinetics, what are needed for the system to do the separation? Okay, so that is what we're going to focus on. I don't know how much time we have left. I think at least I can start this topic. Okay, so now, okay, to answer the questions I just mentioned, we have to take a closer look at the free energy curve. Okay, so again, this is kind of a zoom in version of a very representative double well free energy curve. And in this case, GA and GB are not equal to one another, so we have a slightly asymmetric configuration of the free energy. Okay, so if you do the double tangent construction for this one, x1 and x2 are not exactly the local minimum. They're going to be shifted a little bit due to the asymmetry of the free energy curve. Okay, but that is not the key that we're looking at. So we know that, okay, the system wants to separate, right? So now let's just choose for example, this G naught as my starting composition. Okay, so let me choose X naught. Let me annotate this for you. So which is this guy? Okay, so let me choose this X naught, okay, which I know is definitely between X1 and X2, and thermodynamically, okay, I want to have the separation, right? So, and then let's see, okay, so consider how the separation actually occur. Okay, so we know that most cases in actually all of the phase transformations, the separation is always initialized through fluctuations, right? And then the thermodynamics is going to play a role to stabilize these fluctuations or unstabilize them. So in here we have the same thing, right? So initially you have a very homogeneous mixing of the system, right? Basically, if you look at a small portion, they're going to be uniformly mixed, have a composition of X naught, right? But suppose now in this very local region, I have a small fluctuation in terms of the composition. So this means that, okay, in this region, I have a little bit less solutes. Okay, so I'm losing some solutes. I decrease this to this particular composition. Okay, I don't know, I call this X naught minus. Okay, which is just a little bit to the left to the original composition. And I give the actual amount of fluids to the right region. Okay, I call this X naught plus. Okay, which means that I have a little bit more solutes compared to X naught. And then this is the point I have here. Okay, does this make sense? Okay, we have a fluctuation. Initially, everything is homogeneous. We have X naught as our average composition. Now I start the separation processes by introducing some very small density fluctuations or concentration fluctuations. So I have a left region with a little bit lower composition than the right region. Okay, and of course, these two add up together to X naught, right? Because on average, you still have the same composition. Now, what I want to see is that after this, small fluctuation, do I increase or decrease the free energy? Okay, this is a clear question. Now, if I initially I'm starting from here, right? But now if I, separate the system, locally, right? I start this small perturbation, by decreasing the composition a little bit, and in the nearby region, I increase the composition a little bit, okay? And how this process is going to change the overall free energy. Now, I'm just considering the thermodynamics. That's, for now, do not worry about the interface, okay? Because this is just a kind of a, the microstructure does not change, right? It's just a small fluctuation of the composition. So we don't have to worry about interface at this stage, but we do have to look at interface later. Okay, now we just look at bulk free energy. Do you think that if I start with X naught, do you think that this separation lower my overall free energy or increase my free energy? Any ideas? If we have a system like that, okay, how would you get the free energy for a system like that? If I give you a system like in the regular solution, if I give you this part is A and this part is B, if we forget about the interface for now, I tell you the free energy for A is GA and the free energy for B is GB. How would you compute the free energy of the whole thing? If their molar fractions are 0.5, 0.5, for example. If I give you this setup, how would you compute the free energy of the whole system? This phase separated A plus B. We just take the molar fraction, right? XA times A plus XB times B, right? Because it's just literally, you grasp A and grasp B and put them together. So you just compute the molar fraction for each of them and do a linear combination. Does that make sense, everyone? Okay, and here we have a similar scenario, right? We have X naught minus and X naught plus. They're very similar to this case where you have A on the left and B on the right and have equal molar fraction. So how will you compute the molar free energy? I'm sorry, the free energy for this thing? You just do a linear combination of the two free energy, right? But how can you reflect that linear combination on the face on this free energy plot? This is your, free energy for X naught minus. This is free energy for X naught plus. You literally have a line connecting this two, and then this intersection gives you the free energy for this, phase separating quotation mark small system. Does that make sense to everyone? Okay, so this is exactly the same way of you getting free energy for even the equilibrium case, right? You have a double tangent construction and you have this straight line telling you the linear combination of the free energy, and then this X naught simply determine the fraction of molar fraction for each of the phases. So this is going to be your free energy in the equilibrium case. In here you have the same thing, right? You have A and B. You just do a straight line connecting them together because the free energy is going to be a linear interpolation between the two, and then there's going to give you the fraction. Okay. I hope this is clear. Okay, this is a very old concept that we've seen many times. So anyway, the point here is that, okay, so we start with X naught. Now I have a small perturbation, allow the system to separate into a little bit higher compensation, lower compensation cases. But once I have that separation, do I increase or decrease my free energy? This is my question for you. Okay, I went through all the analysis. Now I just want you to tell me, based on this analysis, do you have increase or decrease of the free energy? Initially, I started this mixing state. Now I'm in a phase separate state. Does this process increase the free energy or decrease free energy?
Decrease.
Decrease your free energy, right? Because this is your new free energy. This is where you start from. So you have a decrease of free energy. And this decreased free energy serves as what? As the driving force, right? So you see that, okay, I start with a small fluctuation, but this small fluctuation does not increase the energy, at least for the particular X naught I choose. It immediately decreases free energy. So there's nothing to stop me to keep on doing this separation, right? As you can probably see, Okay, this is we start from here. This is just separate very smallly, separate, by a small amount. But I can do this, further. If I separate this amount, okay, or I can separate even more, you see that I always keep on decreasing the free energy more and more until I reach here, right? Until the 2 points, composition reach this point and this point. Okay, that is the furthest point I can go in order to maximize the reduction of the free energy. Okay, so basically this analysis showed us that in the spinolo decomposition, if you start with a very small, density fluctuation, at least for the X naught we're choosing, right? You start with small density fluctuation, there's nothing to stop this. Okay, so just to keep on, increasing the differences between the two composition and keep on separating until they reach the equilibrium state, that you reach X1, X2. Does this make sense to everyone? So we call this spontaneous separation or miscibility gap, which means that if you have a system, okay, prepare at this temperature T2 and have this composition X now within certain range, there's no way that we can mix them. The system demixing spontaneously. Okay, so this is what we, one thing that we can get. Okay, I think I will probably just pointing out another case. Okay, so this is, I emphasize several times that, we have this very nice miscibility gap or spontaneous demixing because we choose this particular X naught. Okay, so now I'm going to just quickly highlight a different X naught, which you have a different scenario. Okay, so now if I choose a different X naught, I don't think I have time to finish this, but say I choose this X naught. I think I need to move to the left, but it's okay. I choose this X naught, okay? And I consider exactly the same analysis. This is my X naught, okay? It doesn't really matter where my X naught is. I can always have fluctuations, right? Fluctuations have nothing to do with thermodynamics. It's purely because of stochastic and atomic nature of the system. So I can always have these fluctuations, which is going to give you a slightly higher and lower composition. Now, following the same analysis, we see, this is going to be the slightly lower composition case. This is going to be the slightly higher composition case. Now, if I choose my X naught to be here, and I still have this fluctuation for my system to have a small separation, does this fluctuation increase the free energy or decrease the free energy? Again, if I initially my free energy is this guy, right? But now if I separate into two, faces in quotation mark, my free energy of the system is obtained by first connecting these 2 points and then get the intersection right here. Okay, now following this guide, does this separation increase the free energy or decrease free energy?
It looks like
Increase.
It increased the free energy, right? At least it looks like it increased the free energy. And we can say that, okay, if you think this, okay, this is strange. How about if we keep on and see if the separation continues, that this is also the case? And if you do that, you will see, okay, at least for a wide range of the initial stage of separation, if you want this to proceed, you're always going to increase the free energy. Okay, so this implies that, okay, well, thermodynamically, I have chosen 2 different X naught, one in here and one in here. Well, thermodynamically, they're all within the range of X1, X2, which means that thermodynamically, the system always wants to, has a, tendency to separate. However, you see that, whether the system can actually complete this demixing or phase separation critically depending on where is your X naught, right? So if we choose X naught to be here, there's no, it only feels driving forces. There's no barrier at all. You keep on decreasing the free energy, completely, do the demixing. But on the other hand, if you choose X naught not in a very good location, you see that, okay, although eventually I still wants to separate, because after separation, you see, you're still going to decrease the free energy a little bit. But the entire processes of the separation, basically, involves a large energy barrier, which is not related to any surface, any imperfections. It's related to the free energy curve itself. So intrinsically, if you choose X naught in this region, it has intrinsic barrier, okay, thermodynamic barrier that basically prevent any demixing to occur in reality. Okay, so for the sake of time, I'll just stop here. Okay, in the next lecture, we're going to derive rigorous conditions on how we're going to choose a good composition so that it favors separation, how we're going to choose a bad composition, which, it wants to separate, but never going to actually have that. Okay, so again, I will stop here. So stop recording.